All right, if you recall from the last lecture, we said that probability is the measure of the likelihood that an event will occur. So what exactly does that mean? Now we say it's a measure, but it doesn't really say anything about how we measure it. So what I'd like to do today is get a little more precise in our definition of probability and learn how to quantify it. So let's start out with our simple coin tossing experiment. If we toss a coin, what is the sample space? Now recall that sample space is just the set of all possible outcomes. So our sample space in the coin tossing experiment is just heads or tails. All right, simple enough. And if we toss a coin, we have a pretty good idea of what the probability is of a coin, right? Because those two events are equally likely. So the probability of heads is just 1/2 because it's just one out of two equally likely outcomes. And the probability of getting tails is the same thing because it's just one out of two equally likely outcomes. Okay, so that's an example of theoretical probability. We're just using our knowledge of how coins work and some reasoning to come up with these probabilities. But let's say we didn't know how coins worked, and we were given the task to figure out what the probability of heads was. Then what we could do is we could just toss the coin again and again, and record our outcomes, right? So that's an example of experimental probability. So we're just going to toss the coin again and again and again and observe how many times it comes up heads. And out of the total number of trials that we perform. And so that ratio of the number of times that the event occurs out of the total number of trials is called the relative frequency. And empirical probability is just the relative frequency over a large number of trials. So this table here is out of your book. They've performed an experiment with a coin and tossed the coin 10, 100, 1,000, up to 40,000 times and just recorded the number of heads that they get. And then the ratio of the number of heads out of the total number of trials is recorded over here. Now, if you did this, if you tossed a coin and tried to recreate this experiment, for a low number of tosses, you may not get the same data that they got, right? If you toss the coin 10 times, you might get 6 heads, or you might get 3 heads, you might get 5 heads. You might not get exactly what they got, right? But over a large number of trials, you would expect to get roughly 50% heads and 50% tails. Okay, so that's experimental probability, and oftentimes that's the only kind of probability that we can calculate. Because if you're say in quality control and you're trying to determine what the probability is of a part being defective, then you would have to test a number of parts and then record how many times you end up with a defective part. And so that's really the only kind of probability that you could come up with. All right. So again, the probability of an event is just a measure of the proportion of time that the event will occur in the long run. And it varies between between 0 and 1, right? 0 would be impossible. It would be it's not gonna occur at all. A probability of 1 would mean that it's a certain event, that it's 100% sure it's going to happen. If the probability is greater than 1/2, then it's more likely. The closer it is to 1, the more likely that event occurs. If it's less than 1/2, then it's not as likely to occur. Okay. So let's define got a new piece of vocabulary here called the simple event. A simple event is just an event that consists of one sample point. Okay, so if you recall, an event is a subset of the sample space. And so a simple event is just an event that has one outcome. Okay, and the nice thing about simple events is that they're mutually exclusive, right? So they can't happen at the same time. And we're going to get to that. That allows us to work with probabilities easier. So um, we'll talk about that in a few minutes. Um, what are the simple events in our coin tossing experiment? So if you recall, okay, I can just write this again. Our sample space is heads and tails. So the simple events are heads, right? The single event of getting heads. And the other simple event would just be tails, right? Those are the two subsets, the two single event subsets of our sample space. All right. And once we've got our simple events, then we can calculate probabilities of those simple events. And a probability distribution is just the distribution of probabilities over all the simple events in an experiment. Okay, usually in table form, sometimes in graphical form though. And a probability function is a function that assigns probability to simple events. We're not going to work so much with probability functions in this class. So what is the probability distribution for our coin tossing experiment? Well, our coin tossing experiment only has two simple events. So let's list them. We'll just put it in table form. All right, so I'm just going to draw a little table. And I'm going to list the simple events here. And the probability over here. Probability. Okay. So one simple event is just heads, and the probability of that is a half. The other simple event is just tails, and the probability is 1/2. Okay? All right, so let's go on and talk a little bit more about probability. Now, these are some properties that are out of your book. All right, so this gets a little bit cryptic. There's a lot of notation here, a lot of mathematical notation. But hopefully, I can show you how to translate these into English. So if we have a sample space, right? S is the sample space, and those S1, S2, S3, those are all of our simple events, kind of our general case. The probabilities, the probability of simple event 1, the probability of simple event 2, the probability of simple event 3 have these properties, okay? So these probabilities of the simple events are always between 0 and 1, which we would expect. So that's what this is saying, really, is that the probability of a simple event is always between 0 and 1. All right, so the probability of a simple event is between 0 and 1, just as we would expect, right? Because all probabilities are between 0 and 1. Also, the sum of all of the probabilities of the simple events add up to 1. So essentially, there's a 100% chance that something's going to happen. Something in the sample space is going to happen. Which makes sense because, if we've got a complete list of all of the simple events, right, all of the simple events in the sample space, which are all of the possible outcomes, then it's just saying that it's certain that we're going to get some sort of outcome, right? So that kind of makes sense. Now, this next property just says that the probability of simple event I or simple event J, that one of those two occurs, is just the sum of the probabilities of the two events. Okay? And that's nice. The nice thing about mutually exclusive events is that we can add their probabilities. Now, sometimes those probabilities are different and sometimes they're the same. Now, when we have a sample space in which all of the simple events are equally likely, we call that a uniform sample space. Okay, so each outcome in the sample space is equally likely. So our coin tossing experiment was a good example of that, right? We had two outcomes and they're both equally likely. But also, like rolling a die, that would be another example of a uniform sample space. When you roll a die, you're either going to get a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And each one of those is equally likely. And so when we have a uniform sample space and we've got n possible outcomes, then the probability of each outcome is just 1 out of n, right? So that makes sense because we have, n possible outcomes. Each one is equally likely, so it represents 1 out of n possible outcomes. All right, well, that takes care of this introduction to this section on probability, and I will meet you in the next example.